Hello and welcome to Cashmatics. This is number 5 in my series of lessons on complex numbers, and in this tutorial we will be looking at how we can use complex numbers to express loci and how we can use Cartesian equations to solve loci problems. Now we will need some background knowledge first, which you'll be covering in more detail in your regular Maths A level, but I'll quickly go through it so you understand the core principles behind what we'll be doing. So grab yourself some paper and a pen and let's get started. Right, so before I begin, I'm going to explain what loci is. There was a student who asked me today, what is loci? And I said to him, think of it as a sort of mathematical restraining order. So imagine somebody isn't allowed within 2 miles of your house. Then that person's loci will be anywhere which is outside of 2 miles of your house. So imagine a big circle around your house which is 2 miles in radius. If he steps in there, he's breaking his restraining order and wouldn't be allowed any closer. Anyway, I hope that helps it make a bit more sense. The first thing I'm going to go through is the equation of a circle, and up till now you've probably only seen circles with the centre at the origin, and the equation of a circle at that would just be x squared plus y squared equals r squared. But what we need to know is how to express a circle which has got a centre other than the origin. So imagine you had a circle with a centre AB and a radius r. Then the equation of the circle would simply be x minus a all squared plus y minus b all squared equals r squared. So that's a circle with a centre AB and radius r. So let's just have a look up here at this question. So for example, on this one here, x plus 5 all squared plus y minus 2 all squared equals 12. This would mean that the centre is at minus 5, 2, and the radius would equal the square root of 12, okay, which you could express as 2 root 3. If I started with this instead, so I had the centre and then the radius, I could turn that into an equation. So x minus minus 1, so x plus 1 all squared, add y minus 4 all squared is equal to 5 squared, which is 25. Now sometimes you might have an equation like this, and what I need to do here is complete the square. So let's just write this in a slightly different order. X squared take away 4x, add y squared, add 8y minus 5 equals 0. I'm just going to complete the square for this part here, so that would be x minus 2 all squared take away 4, add, now I'm going to complete the square for this bit, y add 4 all squared take away 16 take away 5 equals 0, and let's just rearrange things slightly. So x minus 2 all squared, add y add 4 all squared. Now minus 4, minus 16 and minus 5 make minus 25, and if I move that to the other side I get 25. So in this case the centre will be at 2 minus 4 and the radius will equal 5. Right, the next thing we need to know is how to work out the equation from off a line given the gradient and any point on that line. And you may have seen this, and if you haven't seen it yet, you will come across it soon. So please remember this, and you'll find it's actually really useful. So what you do here is you leave the y and the x alone, and this y1 and this x1 comes from the coordinates of the point that you know, and the m is the gradient. So I'll show you how it works with this information here. So the first thing I always do is just write y minus y1 is equal to m x minus x1, and that's a habit I've had ever since I was doing it myself at A level, and I write that even though I know it off by heart. So let's just plug this information in. So I'd get y take away minus a quarter, so that would be y plus a quarter, is equal to m, which is minus 2/3, and then I've got x take away x1, which is 3. Now I've chosen these awkward numbers on purpose to show you how you can deal with these awkward numbers. So the first thing I would do is just try and get rid of my denominators, and I'll do it step by step. I could multiply the whole thing by 12, but I'm not going to. What I'm going to do is I'm just going to multiply by 4 first. So multiplying by 4, I get 4y plus 1 is equal to minus 8 over 3 and that would be x minus 3. And then now I'm going to multiply by 3, so I'd get 12y plus 3 is equal to minus 8 x minus 3, and I'm just going to expand the brackets. 12y plus 3 is minus 8x plus 24, and then what we normally do is have it in the form ax plus by plus c equals 0. So let's just move everything to the left hand side, and I'll get 8x plus 12y, and I've got 3 take away 24, so minus 21 equals 0. On the right, we've got a slightly trickier example. What we're going to try and do is work out the equation of the perpendicular bisector of those 2 points, so minus 2, minus 5, and minus 6, 7. So before I do anything, I'm just going to roughly sketch where the positions of those are going to be relative to each other. So 2 minus 5, 2 across, 5 down, so something like that. It doesn't need to be exact, just giving you a rough idea of what's going on. And minus 6, 7, so minus 6, 7, somewhere up here. Okay, I'm just going to join those two with a line, and I'm just going to put a little bit more information on there. Okay, so I'm just going to put a dotted line from here to here. Okay, and look at these distances. So 7 and minus 5, so that is 12. Minus 6 and 2, and that is 8. Okay, and the perpendicular bisector, if you remember the definition from GCSE, is a line which is at right angles to this white line, which goes through the center of it. Okay, so let me just draw that on. So something like that. Okay, so we're trying to work out the equation of this solid green line. So one of the first things we can do is work out the midpoint of these. So the midpoint is equal to, now if you remember, what you do is you take the mean of the 2x coordinates, so 2 add minus 6 makes minus 4, divided by 2 is minus, 2 take away 6 is, minus 4, divided by 2 is minus 2. Okay, and minus 5 and 7 is 2, and divide that by 2 gives me 1. Alright, so that's the midpoint, and the gradient is equal to, so this is the gradient of the gradient between the 2 points. That would be minus, because we can see it's a negative gradient, minus 12/8, which simplifies to minus 3 over 2. But therefore, the gradient of the perpendicular, let's make this a little bit tidier, the gradient of the perpendicular would equal 2/3, because remember, that's the negative reciprocal. So if you know the gradient of a line, all you do is take the reciprocal and change the sign, and you get the gradient of the perpendicular. Right, so what we need to do is use this information and this information into our formula, so the y minus y1 equals m into x minus x1, to work out the equation of the line. So let's put all that information in. So y minus y1 is equal to m x minus x1, y take away 1 is equal to 2/3, x take away minus 2, which is the same as x plus 2. I'm going to multiply everything by 3, so 3y take away 3 equals 2x plus 2. Expand the brackets, 3y minus 3 equals 2x plus 4, and all I'm going to do is rearrange things now. I'm going to move everything to the right hand side, so 0 equals 2x minus 3y plus 7. Well, the next thing we need to look at is some circle theorems. So we've got a circle here, and what you should already know is that if you've got a point outside the circle, if I drew a tangent to the circle on this side and on this side, these two lengths would be the same. You should also know that if you've got the center of a circle, if you draw a radius from there to where the tangent meets the circle, that makes a right angle, so that's a right angle and that's a right angle. And obviously these two, because they're both radii, they'll be the same length. And also, if I was to draw a line from this corner to the center of the circle, this angle here would be the same as this angle over here. Okay, and all these details are really important. The next circle theorem I want to go through is quite an easy one. So this is a circle over here, that's the center, and imagine you were over here. And imagine that was a really nice, inviting swimming pool in the shape of a circle, and you couldn't wait to get in, so you wanted to work out the shortest way to get in. And imagine there was a pole in the middle of that pool, or a fountain or something. The quickest way to the center of that, sorry, the quickest way to the pool would be to aim for that center, right? So if you aimed for there, this length here would be the shortest way to get to the pool. So all you need to think about is if you've got a point outside a circle, the quickest way to get to the circle is to head for the center of the circle, and you'll get there in the shortest, using the shortest distance possible. The last of the things we need to go through is just something about vectors, something really basic, but I need to cover it just in case. Imagine you've got 2 points, A and B. The vector OA takes you to A, the vector OB takes you from O to B, and I want to know what the vector AB is. So AB, to get from A to B, I can go backward along OA and then along OB. So minus OA plus OB, okay, and normally we write that the other way around. Okay, so OB take away OA, all right, and that's a standard result which is used quite a lot. Now we can apply the same thing using complex numbers, because if you remember from one of my earlier videos, the position on the Argand diagram for a complex number can be expressed using a vector, all right. So if I want to get from Z1 to Z2, okay, so Z1 to Z2, okay, what I can do is I can go backward along Z1, then along Z2, okay, so Z1 to Z2 would equal Z2 take away Z1, okay, so backward along there, so backward along Z1, so minus Z1 along Z2, so that would be a positive Z2. Now this is going to be really important when we do the next part, so please make sure you've understood what's going on over here. So that is the vector that we're after. Now we're going to apply what we've just seen and try to work out the equation of a circle using complex numbers. So what I'm going to say is let's define this length as R. Okay, so that's obvious, that is the radius of the circle. And this Z is a general point on the circumference of a circle. So I know I've marked it over here, but it could be anywhere on the circle. Now, this R, if that was a vector, okay, the way you'd work it out is you'd go from backward along this one, and then along this one, okay? So R, if it was a vector, it would be minus Z1 plus Z, okay? But what I'm going to do is I'm going to write it the other way around. R is equal to Z minus Z1, okay? Now, if I want R to be constant, so if I want this to be a circle, that would mean that the modulus of this, so that this length, which we work out using the modulus, would have to be constant. So that's the equation of this circle, okay? Where Z1 is the center of the circle, okay, and that is A plus BI. Now it may not make much sense as it is now, but let's just apply it to some real numbers, well, some complex numbers. So let's say we've got a center, and the center is at 3 plus 5i, and the radius is, let's say, 7. Okay, so what this is trying to say is that the modulus of Z take away 3 plus 5i is equal to 7. Okay, now you'll notice it's not equal to 7 squared, it's equal to 7. You square it when it's in Cartesian form, okay, not when it's in complex form. So what we can say from this, if I wanted to work out the Cartesian equation of this circle, I would say, okay, well, I know the center on the Cartesian axis would be 3, 5, and the radius would be 7, which means the Cartesian equation would be x minus 3 squared add y minus 5 squared is equal to 7 squared, which is 49. So this would be the complex version of it, and this would be the Cartesian version of it. Right, I'll do one more example on that just in case that didn't make sense. So let's say we've got the complex number, so the equation Z plus 5 minus 3i equals 10. Okay, so the modulus of Z plus 5 minus 3i equals 10. Now you'll notice this bit isn't in brackets, so I tend to write that in brackets first. So Z take away, so remember it's always going to be Z take away something, and then I need to make this work, so that would be minus 5 plus 3i. Okay, so just check your signs, and well, it's just going to be the opposite of whatever these are. So that means my center is minus 5, 3, and the radius is equal to 10. So the Cartesian equation would be x plus 5 squared add y minus 3 squared equals 10 squared, which is 100. Okay, and if I wanted to sketch that, it'd be quite straightforward. So draw your axes, mark on the coordinates, so 5 minus 3, so 5 across, so that would be at 5, 3 down, minus 3, so that would be the center. And the radius is 10, so it's going to reach both axes. So this is going to be exact, but it'd be, you know, something like that, but just a bit rounder. I know I said I was only going to do one, but here's another one as well. So let's just rewrite this. So z take away. Now this would be 7, so that's okay as it is. Minus 4i equals 5, which means the center is at 7 minus 4, and the radius, oops, let's put this in brackets, and the radius is 5. So the Cartesian equation would be x minus 7 squared add y add 4 squared equals 25. Right, let's have a look at this equation and try to understand what it means. Now you would be forgiven for thinking this is two circles, okay? Because you know, in the last example, that was part of the equation of the circle, okay? But because we've got the title perpendicular bisectors, you might not be forgiven for that. Right, so the first thing I'm going to do is exactly what I did before, okay? I'm going to just write this as z take away 3 minus 4i is equal to, and on this side, z take away 5 add 2i. Wait, that should be a minus 5. And the first thing I'm going to do after that is I'm going to plot the points 3 minus 4 and minus 5, 2, because that was what we did when we, you know, worked out the equation of the circle. So 3 minus 4 is 3 across and 4 down, so something like that. And this here, minus 5, 2, so minus 5, 2, so something over there like that. Okay, something over there. And what this equation is saying is there's a complex number z, so you can see the z here and z over here, so it's the same z. There's a complex number such that the distance between that complex number and this point is the same as the complex number and this point. Okay, so if I was to just draw a line between those, what you should realize from that is that it needs to be along this line here somewhere. It needs to be the perpendicular bisector. Okay, so as long as the complex number is on this line here, it'll always be the same distance away from that point as it is from this point. What you should realize from that is that it needs to be along this line here somewhere. It needs to be the perpendicular bisector. Okay, so as long as the complex number is on this line here, it'll always be the same distance away from that point as it is from this point. So let's go ahead and work out what that equation is. So the first thing we need is this midpoint here. Okay, I'm just going to call it mid. Okay, and remember it is the average or the mean of the 2x coordinates. So minus 5 at 3 is minus 2, divided by 2 is minus 1. Okay, and 2 at minus 4 is minus 2, divided by 2 is minus 1 as well. So that's worked out nice. And the gradient of this this red line, let's have a look. Okay, let's just draw a triangle there. So that is 2, that's minus 4, so this distance is 6. That's minus 5, and that's 3, so this is 8. So the gradient of the red line is minus 6/8, but the gradient that we need, the gradient of the perpendicular, would be 8/6, which is the same as 4 over 3. Okay, so now what we can do is we can plug it all into our equation. So y minus y1 is equal to m x minus x1. So y take away minus 1, so y plus 1 is equal to m, which is 4/3, x take away minus 1, so x plus 1, multiplied by 3, 3y plus 3 is equal to, and that would be 4x plus 1, and I'm going to expand the brackets, so that would be 4x plus 4, and let's just put all that together like this, so 4x minus 3y plus 1. So that would be the equation of the perpendicular bisector, or the point where z needs to lie in order for it to be the same distance away from both those points. Okay, so let's have a look at a more involved question. So this is how a question might be worded in a paper. So the first bit is sketch the locus of z, and the second bit, find the maximum value of arg z. So I'm going to start this just like before. I'm going to express this as z minus, so that would be 5 plus 3i equals 3. Okay, and what that means is the center is at 5, 3, so 5 across and 3 up. Okay, so that would be there, and the radius is 3, which means this distance here is 3, so it'll just about reach. Well, it will reach the axis here, but it won't reach the axis here. So that circle is the locus of z, and I'm not going to do it, but you could be asked to work out the Cartesian equation here. That'd be quite straightforward. It'd be x minus 5 all squared add y minus 3 all squared equals 9. Okay, that's straightforward. I've done enough of those for you to know how to do that. Then the next bit is find the maximum value of arg z. Now remember, z is always measured from here. Okay, so any complex number z starts off at the origin. Okay, so what it's asking me to do is find a point such that the angle from the origin to the circle is as big as can be, and that's going to be when it hits the circle here. Okay, so this is the biggest argument. Any bigger than that and you won't touch the circle, any smaller than that, well, and it's not the biggest one. Alright, so what I can do is I can use one of my circle theorems. So if I draw a line to there, okay, and then draw a line there and there, I can use one of those circle theorems that we looked at earlier. Alright, so if I was to work out this angle here and double it, I'd get my argument. And the reason I can double it is because this angle here, this black one, is the same as this one over here. Sorry, this white one is the same as this one over here. Right, so let's just say this is theta. Okay, so theta would equal the inverse tan of 3/5. Okay, so therefore the argument of z, so this is the maximum argument of z, would equal twice that. So 2 multiplied by the inverse tan of 3/5, which equals 1.08 radians. Right, here's one more question. We've got the modulus of z take away 12 minus 5i equals 3, and it says find the maximum value of the modulus of z and the minimum value of the modulus of z. So I've tried to save us a bit of time by just doing this bit first. I'm sure you're familiar with what I've done there. I'm just going to mark on this point, so 12, 5, so 12 across and 5 up. Okay, so that's 12, 5. So the centre of my circle would be there, but because my radius is only 3, the circle's not going to reach either of the axes. So what does the question actually mean? Remember, z has to lie in the circle, and what the question is asking is what is the shortest distance from the origin, which is here, to this circle. Right? And as I showed you with one of those circle theorems, if you were to draw a line heading straight for the centre of the circle, through the centre, not like that, so through the centre of a circle, second time lucky, there you go, brilliant. I'm just going to mark on some points, so let's call that A, let's call that C for the centre, and let's call that B. Now Z min is equal to, this is the origin, remember, is equal to OA. But OA is equal to, now I need to work out what I can actually find. I know I can work out what the distance between O and C is by using Pythagoras, because I know this is 12 across here, okay, and that is 5 across there. So I can use Pythagoras. So OC take away AC. Okay, now AC is the radius. Okay, so that would be take away 3. And OC I can use Pythagoras to work out. So that would be the square root of 12 squared plus 5 squared. Okay, so that would be 13, take away 3, which is 10. And Z max is equal to the furthest point on that circle, so OB. Now OB is actually quite straightforward. If I already know what O to C is, okay, so just write that down, OC plus CB, and OC I've just worked out, we worked it out over here, is 13, plus CB, which is just the radius, that's another 3, that would be 16. Right, and that's it. I hope that's given you a basic understanding of how to use complex numbers to express loci, and how we can use them to work out perpendicular bisectors and various other bits and bobs. And I'm sure there'll be more detailed questions in whichever exercise book you're using, but that's the foundation of it all, and I hope that's helped you. So that's all for now. Next lesson we'll be looking at how we can express regions on the Argand diagram using complex numbers. So they're more loci problems, but they're regions rather than lines. Okay, so it might be the modulus of z take away some complex number is greater than 3, or less than or equal to 3. So it'll be within the circle or outside of the circle. Or if it's to do with a line, it'll be above the line or below the line. Okay, and we'll look at how we can express those on the Argand diagram. But for now, thank you for listening, and I'll see you next time. Goodbye.